All right, welcome back from spring break, everybody. Couple reminders as we begin today. Don't forget there are no more daily quizzes, so don't worry about that. And your polar coordinate system, my math lab quiz, that's on the stuff we're about to go over, is now available and due on Monday, the 27th at 11:59 p.m. All right, we're going to start a new chapter. We're actually going to start in the middle of chapter 6 and then just talk about polars and not talk about vectors due to time constraints. So let's talk about polars. And if you want or remember from the intro information, polar coordinate system is basically taking that linear system and turning it into a circular design. So when we talk about a line graph now in polar coordinates, that's going to be a circle. And if we were talking about some kind of curve, like a sine curve or a cosine curve, then that's now going to give us a new shape on this polar coordinate system. So today we're going to go over the basics and how to graph a point on that coordinate system and find all the other points on that coordinate system. So we're going to start, and basically a polar coordinate system is a plane, just like your Cartesian plane, your XY graph. But this time we're going to talk about our point 0 or O being the pole or the origin, and then all of the rays that extend from that point O. So when we think about any point in the coordinate system, we're talking about some ray that comes off of point O. And when we find that particular point, we need two kinds of measurements. So just like in a Cartesian plane, we needed an x distance and a y distance, or a horizontal and a vertical distance. In a polar coordinate system, we need two things. The value r, which is your distance from the pole, and then your theta value, which is your angle of rotation that you've moved. So those are the two things you're going to need to graph a point in polar coordinates. You can kind of see down here, here's our basic polar graph. So we start with any pole, and then you take that ray and you're going to rotate it up to 2 pi or 360 degrees around that pole in any position. And to find a specific point, we're going to find that r value, which would be the distance between the pole and the point, and then your theta or your amount of rotation that you're talking about here. A couple of basics, just like we talked about XY basics when you first learned how to graph. For polar coordinate system, there are set amounts that you would go through on your radius value or your R value. So we have 1, 2, 3, 4, 5, etc. That would be your distance out. Likewise, you could go backwards, and we'll kind of talk about that in a minute, but this would be then -1 here if you go backwards. And then each of your theta values are split up into 6 different groups per quadrant, or 12 different groups for the semi-circle. So if you count from what we would normally start at as 0 degrees all the way to pi degrees, then you'll find out there's 12 different sections. That makes each of these lines pi over 12 or 15 degrees. And then as you go up, you will add more pi over 12s together and then reduce that to get you your typical measurements that you would find on your unit circle. So as a reminder, this 15 degrees is not normally on our unit circle, but 30, 45, and 60 are. So that's kind of your basics of your polar graph system. They're all going to look exactly like this, where you can count for your R value 1, 2, 3, negative 1, 2, 3, and then you can do your circle theta distances around as your angle rotations. Okay. All right, so let's take a look at some example problems. So if our point is 2 comma pi over 3, that tells us that our r value is 2, and we are going pi over 3 degrees in our theta rotation. So if you look at my circle over here, starting at the pole, or 0, I would go out 2, so that would put me right here on this second circle, and then I would rotate regular counterclockwise pi over 3 degrees, or 60 degrees if you're changing that to degrees. That gives my point right here on that second circle at that pi over 3 line. So that's pretty easy. Things get a little more complicated when you change either your R value or your rotational value. So our next example you'll see has a negative R value. That means you have to go to the left when you start counting for your R. So you go back one or to the left one, and then remember we're still rotating counterclockwise because 3 pi over 4 is still positive. So from that -1 point, we're going to go counterclockwise 3 pi over 4 spaces. So I'm going down, and yes, this is not normally pi over 4, but from here at the negative point, that is going to be pi over 4 degrees. And then there's 2 pi over 4, or really pi over 2 from that point, and that makes 3 pi over 4 here at that Q point. So Q, this dot right here, is -1 comma 3 pi over 4. So this is positive R, positive angle. Q is negative R, positive angle. Does that make sense? Okay. From there, let's talk about negative angles. So in our third example, we have a positive R value and a negative angle. So remember, negative angles are actually going clockwise instead of counterclockwise, but the 3 says go to the right first. So I go 1, 2, 3 to the right, because that's positive, and then I go clockwise 45 degrees, so that would be down 45 degrees, and that gives us our R value here. All right, let's take a look at a couple more points. So if you take a look at each of these, here we go with our new point S. Again, we're going to the right, and just like the one above it, we're going clockwise pi over 3. So if I go 1, 2, 3, 4 circles out, and then go through and go down pi over 3, that gives me that point S right here. T is to the left 3, but now because we are going in a positive theta direction, I'm going to go back counterclockwise. That would be, sorry, in this direction. So I'm going to go all the way down the bottom of the circle and then plus a little more. Notice 3 pi or 13 pi over 12 is a whole pi rotation plus 1 pi over 12. So 12 pi over 12 plus 1 pi over 12. And remember, 12 pi over 12 is that whole semicircle. So that's why my T ends up being here when I started way over here on the left side. So I went all the way around to the right side and then up a little more. Finally, the last one is negative R and negative theta. So I'm going to go to the left 5, and then I have to go clockwise 4 pi over 3. So I'm going to go around like a clock. So I'm going to go up first. Pi over 3 would be here, 2 pi over 3 here, 3 pi over 3, 4 pi over 3 would be right here. So that's how I get around to R. So if you think about it, I started over here and I actually went all the way around this way for V. Sorry, that should say V and not R. My apologies. V. All right. All right. So hopefully that helps as far as graphing goes. To the left or to the right for your R value, and then clockwise or counterclockwise for your theta value, and just making sure you're counting or looking at that pi over 3 or pi over 12, sorry, increment when you do your thetas. All right. Now, one of the other things we're going to talk about when we talk about our polar coordinate system is not only being able to graph those points, but also describe all of the other points that would be equivalent to that. And when we did that early in trig, we talked about coterminal angles, and coterminal angles were the same amount of same angle but a different amount of rotation. So instead of going clockwise, maybe we went counterclockwise, maybe we went clockwise plus some, or counterclockwise plus some, etc. So you can find those coterminal angles. For example, if I started with pi over 4, then the the clockwise value would be -7 pi over 4. So I could go up pi over 4, or I could go around -7 pi over 4. The other option for describing your angle is to go from your opposite R value and then go an additional half circle. Remember, a half circle is pi rotations. So it looks like this. if I started with any random point, that would be some r value with some theta. So that's this green dot right here. Then I could write my coterminal as being from that same r value, but around the other way. So from 2 pi backwards. So that would be theta minus 2 pi or theta minus 360. Another way to describe that would be to go to the left or have that opposite r value and then go around a half circle plus whatever my theta might be. So I started at the left side here, so I have to go pi degrees around to get back to the regular, and then another theta to come back to that green dot I started with. And then finally, the other angle you could write there would be to start again at the left, but this time find that coterminal angle. So just do pi or theta minus pi for that value. Okay, so we'll show you kind of a number example for that here in just a second. One of the other things you can write, just like writing all of these coterminals and opposite R values, is to give all the polar coordinates. So this would be 3 specific up here, or 4 specific if you counted the original. But to find any polar coordinate, remember you can go infinitely many times around and around and around the circle. So if you look, obviously you have r and theta. Then this would be your coterminal angles, 0 plus 2 pi n. And then you could do your opposites and have 0 plus 2 pi or plus 2n plus 1 pi. Why do we have that extra 1 there? Remember when you went to the left, you had to go all the way back around pi degrees to get back to the original, and then you would continue on that theta amount. Now I have simplified this negative r value. I think that's a little easier to understand. So first I distributed my pi's. So I had 2 pi n and then pi. So you'll see over here, I still have my negative r and I still have my theta, but now I'm going to add to it another pi. So that would be the bottom amount. And then another 2 pi n to go all the way around the circle infinitely many times. Okay. So let's take a look at an example. Let's start with 3 and pi over 3. So if I graph 3 and pi over 3, I went out 3, and then I went up to pi over 3. So that's my original point P. Everybody okay there? All right, now my coterminal would be to go out 3 and then go back around the other way. So if you look, I went out 3, and then I went around the other way, which would be negative 5 pi over 3. How did I come up with that value? Well, I did pi over 3 minus 2 pi. You're going to have to change your 2 pi there to be common denominators. So it's really pi over 3 minus 6 pi over 3. And that's how I got my negative 5 pi over 3. So that's your coterminal angle with this original point. You can see the green point P, and then to go backwards around the circle would be the coterminal angle. Okay? Now, you can also write your opposite r value. So that means instead of going to the right 3, we would go to the left 3. So you can see now I'm starting over here. I have to go a full pi and then another pi over 3 to get back to my green dot. So that full pi is really 3 pi over 3. And then I went the another pi over 3 for my theta rotation. So that's how I got this 4 pi over 3. It was pi plus pi over 3, or 3 pi over 3 plus pi over 3. And then finally, if I start at negative 3, I can find its coterminal. So I'm going to go through there and do pi over 3 minus pi to get that negative 2 pi over 3 value. All right, let's talk about finding all the polars. So notice this one just gave you a number of some amount of polar coordinates to find, 3, 4, 2, whatever. If it asked for all, then that's when you know you have to throw this n in there to stand for any integer, which means it could happen again and again and again. All right, so our first coordinate is 2 and pi over 6. I went ahead and graphed that. And then basically, if we wanted to find all the coordinates, we could start at 2, we could go to pi over 6, and then we could go infinitely many times around the circle. So we have 2 pi times some number, some integer number that we want as many times around the circle. So pi over 6 plus 2 pi n. Now, if we wanted to go the other way and start at negative 2, then remember we'd have to go a full pi to come back, and then another pi over 6, and then go from there all the way around 2 pi 2 pi n, 2 pi n, okay? So I wrote that here. I have my pi over 6 plus the half circle pi that I need to go to come back to the right side when I start at -2. And then from there, I'm going to go 2 pi n, 2 pi n, 2 pi n. You want to simplify this, though, because you have your pi over 6 and your pi. Those are like terms. Notice neither one of them have an n like this one does. So I'm going to add 1 pi over 6 and 6 pi over 6, and that's how I got my 7 pi over 6. So 2 comma pi over 6 plus 2 pi n is all coordinate values, and -2 comma 7 pi over 6 plus 2 pi n would be ways to describe all of those green points infinitely many times around the circle. Okay. If we take a look, there's one more, this time in degrees. So really all I did was change my 2 pi's to 360s. I started at -2.5 comma 50. I kind of eyeballed this one because there's not a 50 degrees and there's not a 2.5 circle. So I went to the left 2.5 spaces, and then I eyeballed about 50 degrees rotation. Remember, you're still going in that counterclockwise direction because it's positive 50 degrees. So then when I go through and add my values to go all coordinates, I'm going to add those infinitely many circles, so plus 360n. You cannot add these because remember this one has no n and this one does have n. So 50 plus 360n is your total value of all of the infinitely many circles you can make with that degree or amount of rotation. Then for my opposite r value, now I'm at positive 2.5, so I went to the right. This time we have to go 180 degrees. My apologies. 180 degrees this way, and then around and around and around and around to get to that point. So I have my 180 to do that half circle to get back to the beginning, and then 360 for all the infinitely many circles. Notice the 50 and the 180 both have no n on them, so I need to combine those and start at 230 degrees and then go around infinitely many circles. If I started here at 2.5, you can envision too that it would take me 230 degrees to get to that point Q, and then I would go around and around and around for each of those circles. Okay, just a reminder that we will have office hours on Thursday. If you have any questions on this and you need anything for those. And on Thursday, we'll have a new set of notes, I think on changing from polars to rectangulars is our next one, I'm pretty sure. If you have any questions, feel free to email me tomorrow from 10 to 12 or Wednesday from 10 to 12, and then virtual office hours on Thursday.